second gas law we're going to look at is Charles's law. And Charles's law is what happens when about the volume and the temperature. And in this case, we're got to keep the pressure the same. Okay? Got to keep the pressure the same. Now, what we're going to do is, as you can see, there's some flames under this box. Ooh! Which means the temperature's going to rise. But if we've got to keep the pressure the same, what's got to happen to the volume? Well, let's see what happens when we keep the volume the same and the temperature goes up. Ooh! Ee! Ah! Ee! Ooh! Ee! Ooh! Ee! Stop! 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 Well, what happened there was, when the temperature went up and the volume stayed the same, we bounced off the walls and we bounced off each other, which means the pressure went up, and that's no good. So what have we got to do to keep the pressure the same when this funny little flames tickle us from below? Have a guess. Well, the challenge was to try and keep the pressure the same while these flames tickle us from below. Now, if you've guessed that we need to increase the volume of this container, you were right. Look, let's start off in this normal sized container. Watch it as bouncing off the walls. Ooh, ee, ooh, ee, ooh, ee, ooh. Now, the Bunsen comes on underneath, but let's double the size of the container. Ooh, ee, ooh, ee, ooh. Ah, that did it. We kept the pressure the same. That was a demonstration of Charles' law, the volume being directly proportional to the temperature when we keep the pressure the same. See if you can remember that one.
Let's take a look at the relationship between pressure and volume of a gas. To do this, we're going to imagine that we have a container similar to ones that we've looked at before, where I've got a plunger on one end. This container is filled with gas particles, which I'll indicate as usual by these red circles here. Right now, the pressure on this gas sample is relatively low. P stands for pressure. But as we've learned previously, because gas is compressible, I can put pressure on this piston and I can push it further into the container. And what's eventually going to happen after I've increased the pressure there is that I'm going to have all these gas particles squeezed into a much smaller area. So over here, the pressure is much higher. Let's look at what happens to the volume during this change. Volume right here, relatively speaking, is pretty high. These gas particles have a good amount of room to move around in. On the other hand, the volume over here is pretty low. We've squeezed them into a much smaller space. So as pressure goes up from low to high, volume goes down. What this means is that the relationship between pressure and volume is an inverse relationship. As pressure goes up, volume goes down. They move in different directions. On the other hand, if pressure were to go down, the volume would be able to go up. You're familiar with an inverse relationship because you see this a lot with the cost of things that you buy. As something becomes more expensive, fewer people want to buy it. On the other hand, as the price of something lowers, more and more people want to buy it. So that's an example of an inverse relationship too, things moving in different directions. Pressure and volume also move in different directions because they have an inverse relationship. Let's look at how we can actually plug numbers into an equation and use this relationship to solve math problems. The relationship between pressure and volume of a gas is described by Boyle's law, which is named after the scientist who figured out what the relationship between pressure and volume of a gas was. Boyle's law can be stated that P1 times V1 equals P2 times V2. Boyle's law assumes that we have a gas and it experiences some sort of a change. Maybe we increase or decrease the pressure, change the volume in some sort of a way. So P1 V1 means that the pressure and the volume before the change multiplied together, so here we have before, equals the pressure and the volume after the change multiplied together. So let's move right into an example of a math problem that we might do to see how we can use this. I think it'll make a lot more sense. Here is a sample problem. We say here at 1.70 atm, a sample of gas takes up 4.25 liters. If the pressure on the gas is increased to 2.4 atm, what will the new volume be? So as we said before, there's a change that takes place. We increase the pressure. We now want to look at the before of the gas and the after of the gas, figure out which of these variables we need to solve for. Okay. At 1.7 atm, a sample of gas takes up 4.25 liters. So we have the before pressure, 1.70 atm, and we have the before volume, 4.25 liters. We now say if the pressure on the gas is increased to 2.4 atm, what will the new volume be? So we have P2, we have the second pressure after the change, we don't have the volume. So it's going to be V2 that we're going to be solving for. We'll want to rearrange this by moving P2 under this other thing. So we're going to get P1 V1 divided by P2 equals V2. And now let's go ahead and plug in our numbers. Initial pressure is 1.70 atm times initial volume, which is 4.25 liters, divided by the second pressure, which is 2.40 atm. Now let's take a look at how we set this up. ATM's up here, ATM's down here, which means that the atmospheres are going to cancel out. We're left with liters, and our final answer is going to be 3.01 liters. Before we call it quits, let's see if this makes sense. Well, we started at 4.25 liters, and we increased the pressure on the gas, which means that we squeezed it into a smaller space. So 3.01 liters is less than 4.25 liters. This makes sense that we'd have a smaller volume after increasing the pressure. Now, if you need to learn more about Boyle's law, how Boyle figured out this relationship in the first place, or want to look at graphs, or have seen something in your textbook that says P times V equals K, go ahead and look at the more complex Boyle's law video. Otherwise, you can just move on to the next gas law videos.
Avogadro's law talks about the relationship between the amount of gas that's in a gas sample and the volume of the gas sample. So what does that mean? Well, first of all, a gas sample is just a fancy term that means a bunch of gas we have anywhere. So for example, this balloon has a whole bunch of gas in it that is what's keeping it inflated. So the gas in here can be considered a gas sample. This gas sample, the balloon, has both a volume. It takes up a certain amount of space that we could measure, and there's also a certain amount of gas inside. When I talk about the relationship between these two things, all I mean is what happens when I change one of them, what happens to the other. So let's talk about this. Let's imagine that I have my balloon and investigate the relationship between these two variables, okay? Here is a real quick drawing of the balloon, okay? So, talk about the relationship here. Let's say that I untie the knot at the end of the balloon and I blow more air into it. That is going to increase the amount of gas that's in that balloon. So, we'll say that little n, the symbol that we use to indicate the amount of gas, little n goes up. So, the relationship, what effect is that change going to have on the volume of the balloon? Well, okay, this isn't exactly rocket science. It's going to make the volume of the balloon get bigger. We increase the amount of air, the amount of gas that's inside, the volume goes up. So N goes up, and V goes up as well, okay? Let's look at the opposite case. I untie the knot at the end of the balloon, and I let a whole bunch of gas out. So in that case, little n is going to get smaller. And what effect is that going to have on the balloon, on the volume of the balloon? Well, the balloon is going to shrink. It's going to take up less and less volume. And here's our baby little balloon here. So the volume has gone down. So here's a relationship. When one of them goes up, the other goes up. When one of them goes down, the other goes down. What's this kind of a relationship called? You may already know. This is what we call a direct relationship. It's when two variables move in the same direction. And we can show this relationship with a graph here. Here on the x-axis, I have the amount of gas, which is in moles. We'll talk about that later, but that's usually how we measure the amount of gas in something. Amount of gas here, and on the y-axis, I have volume. As we increase the amount of gas, the volume goes up as well. And it actually turns out that if we double the amount of gas that's in a gas sample, like a balloon, it also doubles the volume, the amount of space that that gas sample takes up. So here's a graph of Avogadro's law. Okay, now one thing is important to keep in mind, and that's that when I was talking about the balloon, I was changing only two things, right? The two things I was changing was the amount of gas, that was one of them, and the volume was the other. There are other things that I was not changing about that balloon, okay? While I was changing the amount of gas, I was not changing the temperature. Okay, it's not like I was letting out gas and I was heating up the balloon. You can't do that. The other thing that I wasn't changing is I wasn't changing the pressure. So it's not like I was blowing up the balloon but then taking it up to the top of Mount Kilimanjaro where the air pressure is much less than it is here down at sea level. So I was also not changing the pressure. So when we're talking about Avogadro's law, the relationship between the amount of gas and the volume, I can change either one of those, but I cannot change the pressure or the temperature of that gas. These are my constants. These are my variables. Okay? There's one thing that I want to show you really quickly, okay? And that is this device that we talk about a lot when we're doing Avogadro's law, okay? You always see pictures of this when in textbooks and stuff when we're talking about Avogadro's law, so that's just why I want to talk about it for a minute. And this is a crazy thing, okay? It's a canister of gas that has a sliding top. And I made one, well, I made a model of one out of a soda bottle, okay? And you can kind of see how this works, that I have, imagine that this is a canister that holds gas, and I got a pipe that goes in that I can add gas into. And then you can see this top. Imagine that this top could slide up and down in here. Okay, so what's the point of this? The reason we always see these guys, and this is usually how they're drawn when we're talking about Avogadro's law, is because they're a way to change the volume of a sample of gas without changing its pressure. This pipe here indicates something that I could use to pump gas in. So imagine that I pump gas in here. That would normally raise the pressure of a container, but not if the top can slide. Instead, the volume changes. I add a little gas in here, and the top slides up. And then I suck a little gas out, and the top falls back down. Instead of the pressure changing, the top slides up and down. So that's why you always see pictures of this kind of an apparatus, this kind of a device. That's a fancy word, apparatus. But the point of it is just that it's a canister of gas with a slidable top that can go up and down, that can change the volume of the canister as I change the amount of gas that's in here without changing the pressure. Okay? So, Avogadro's law is used a lot for math problems. And when we talk about math problems with Avogadro's law, the form of the law that we usually use is n1 divided by v1 equals n2 divided by v2. This equation assumes that some sort of change has taken place, like the change I was talking about earlier. It assumes that I have an initial amount of gas and an initial volume, that's before the change, and then the amount of gas and the volume change after I do something to it. Okay? So, let's work through this Avogadro's law by looking at a math problem here. So, in a sample of gas, 50.0 grams of oxygen gas take up 48 liters of volume. Keeping the pressure constant, remember that's important in Avogadro's law, pressure's got to be constant. Keeping the pressure constant, the amount of gas is changed until the volume is 79 liters. How many grams of gas are now in the container. When I'm doing problems like this, I find it really helpful to keep track of my variables by making a chart like this. I've got my before and I got my after, because we said there's a change that takes place, this little arrow, we're moving from one to the other. Let's get our variables straight before we plug anything into this equation. So, in a sample of gas, 50 grams take up 40 liters. That's what we start with, okay? So that means that N1, I'm going to make that 50.0 grams. That's that. And the volume, it says here that they take up 48 liters of volume, okay? So 48 liters is before the change. Now here's the change. Keeping the pressure constant, the amount of gas is changed until the volume is 79 liters. Okay, so that means that my V2 is going to be 79 liters, the volume after the change. And the question is, how many grams of gas are now in the container after the change? So it's going to be N2 that I'm going to be solving for. So now I got my variables straight. I know what I'm going to be solving for, and I know the other guys. Okay. Now it's important to look at units. There are two things to keep in mind. When we're doing Avogadro's law, this little n always has to be in moles. Okay? Moles is usually how we keep track of the amount of gas we have in a sample. So the amount of gas here was given in grams. That's not going to work. We're going to have to convert it to moles. And this is probably the biggest mistake that people make when they're doing Avogadro's law. They don't remember to convert grams into moles. So hey, if you get a practice problem and your N1 or N2 is already in moles, you're all set. No big deal. You can skip this step. But if you get a practice problem like most of them are, where the N's are in grams, we're going to have to convert it to moles. So we'll do that in a minute. The other thing is the V's. It doesn't matter what units the volume is in, as long as they are both in the same units. Okay, so liters here, we're set. If this was milliliters, milliliters, that would also be okay. But it wouldn't work if one was milliliters and the other was liters. Okay, so volume units don't matter as long as they're both the same. Okay, so now I've got my before and I've got my after. I'm going to change my 50 grams into moles. And in order to do that, I'm going to have to use the molar mass, which tells us how much 1 mole of a gas weighs. Okay? So the molar mass for oxygen is 2 times 16, because each oxygen atom weighs 16. And then we do 2 times that because there are 2 oxygens, and we get 32.0 grams per mole. Okay? So now we want to go from grams, which is 50.0 grams, and I want to multiply this by this grams per mole fraction in a way that's going to cancel out grams. So I'm actually going to want to flip this so that I have grams on the bottom so that they cancel out. Okay? So I'm going to do 1 mole divided by 32.0 grams. All I've done is flip this. Now I have grams up here and grams down here. That means they cancel out. I'm going to be left with moles. And the answer that I get there is 1.6 moles. So I can cross out my 50 grams and replace it with 1.6 moles. Now, I got my N's in moles. Well, I got one of my N's in moles. I got both my volumes in liters, which is the same unit, and now I'm ready to go. So it's going to be N2 that I want to solve for. I want to rearrange the equation to get N2 by itself on one side of the equation. So to get N2 by itself, I want to get rid of the V2 that's in the denominator right now. So I'm going to multiply both sides of the equation by V2. Now I have V2 above V2 down here, which means they cancel out, and I'm going to be left with V2 times N1 divided by V1 equals N2. Some people like having the variable that we're solving for on the left, so I'm just going to switch that real fast, but it doesn't make a difference. I'm just going to put it in reverse here, V2 times N1 divided by V1. Okay? Now we're ready to take our variables that we've laid out here and plug them in. So I've got N2 equals V2, 79 liters, times N1, 1.6 moles, divided by V1, which is 48 liters. And when I do that, the number that I get is going to be, let me check here, 2.6. And what are my units going to be? Well, liters up here, liters down there cancel out. So my final answer here is going to be 2.6 moles. I'm not quite done with the problem yet, though, because my question here asked me how many grams of gas are now in the container, not how many moles of gas. So now I'm going to have to take this mole number and convert it back into grams. How am I going to do that? Well, what I'm going to want to do is I'm going to want to take the molar mass of oxygen again, which, as we said earlier, was 32.0 grams per mole. And I'm going to take my mole number, 2.6 moles, and I want to multiply it by this conversion factor in a way that's going to get rid of my moles. So I can keep the conversion factor just as it is right now, and I'll have moles on the top, moles on the bottom. So 2.6 moles times 32.0 grams divided by 1 mole. Now mole on top, mole on the bottom, they cancel out. And when I do the math, 2.6 times 32, I'm going to get 83 grams, which I'm going to round to 2 significant figures because I have 2 sig figs here and 3 sig figs here. I always go with a smaller number. So I am going to get 83 grams as my final answer. Okay, so that's Avogadro's law. If you have questions on how to rearrange this law to solve for any of the other variables, I've done a video on that. Check out my Rearranging Gas Equations videos. If you have any questions in general about these gas laws, be sure to check out the Gas Laws Extra Help and Frequently Asked Question video, which should clear up any other questions that you have with this sort of stuff.